Okay, our next lesson on conic sections has to do with circles and ellipses, cramming those things together. We're going to, objective 1, be able to define circles and ellipses as conic sections and as a locus definition. And as far as the conic sections go, we've already talked about that, so we'll just review that a little bit. Objective 2, be able to write the equations of the circles and the ellipse in standard form, just like we did with parabolas. And then finally, objective 3, graphing them. You know, because that's what we do. So objective 1, being able to define an ellipse as both a conic section and as a locus, and be able to find all of its parts, all its important parts, like the vertices, the foci, and all of the axes. And as you can see, this heavily tattooed woman here is on a piece of exercise equipment, and that piece of exercise equipment is called an elliptical machine. Let's see why it's called an elliptical machine. Alright, so the story goes like this. There was an engineer who was watching his daughter run, and he noticed that the normal path that his daughter's foot traced out as she was running, it looked like an ellipse. So he put that together to make this thing called an elliptical machine that mimics the more natural movement of your foot as you run, and it gives less pressure on your knees and stuff than a traditional running does. Okay, so what I did in this little sketch is I took the picture. Now the picture is not going to move. The shoe is going to move with this, and the picture is just kind of giving you an idea what this thing's supposed to look like. Okay, so now what I can do is I can move this point E around the circle, just like the elliptical machine would do. It would just go around and around this circle as you were moving your foot back and forth. And notice that your foot is tracing out an ellipse. Now, it's a locus, basically. It's a collection of points that all have something in common, and it's driven by this elliptical machine. And this is why it is called an elliptical machine, is because the shape that it traces out looks like an ellipse. Let me go ahead and show the actual locus. Okay, and I can animate that point so it goes all by itself. Is it a true ellipse? As we'll see when we talk about the definition, it's not, because the major and the minor axis, they're not exactly dead center. But watch something else that cool that happens. Depending on where your shoe is on this elliptical machine, it will look more like a flatter line the closer it is to, let's say, the whatever this thing is called, this lever that's moving backwards and forwards, and the closer it is to the actual circle back there at the back of the machine, then your shoe would be tracing out an actual circle. So that's a pretty cool application of something that is an ellipse. Very interesting, very interesting. Phenomenal Geometry Sketchpad demo. Okay, so remember what a conic section is that we take a double nap cone, which is two infinite cones, put them tip to tip, and we slice it with a really, really super sharp plane. And if we make that plane parallel to one of the bases, I make a circle. That's one of the ones that this lesson's about. And if I take that parallel plane and I just tilt it a little bit, I make an ellipse. Looks like a circle, but I've stretched out the circle a little bit. So the radius is not the same on it. Okay, now we looked at this in the parabola lesson so that you could wrap your brain around what a locus was. Remember, a locus is just a collection of points that all have something geometrically in common. For a circle, what they had in common is if you take a point that's on the plane and all the points that are equidistant from it, that made a circle. Okay, and then we use that definition together with the distance formula to come up with the equation of a circle, and this is in standard form here. This equation is part of what this lesson's about, and you can find it on your nifty flow chart. Okay, so now we're going to do this something similar for an ellipse. So here is the locus definition of an ellipse. So an ellipse is the set of all coplanar points x, y So again, all points in one plane. It's a two-dimensional shape, such that the sum of the distances from that point, in this case we're talking about point P here, the sum of the distances from that point to two other points, which are called foci, so two focuses, plural is foci, is always constant. So in this picture, if I take this point P that's on the ellipse and measure the distance to this first focus and the second focus, and I add those things together, that distance always stays constant. So in this picture, I can see right down below, D1 plus D2 is equal to some constant number for this ellipse. Let's look at that in a little bit more detail on Geometry Sketchpad. So let's examine the definition, the locus definition of an ellipse in a little bit more detail. So remember what it was saying is that if you take a point and measure the distance away from two other points called the foci and add those two numbers up, it's always the same. So on this diagram, if I take point P and I just move it around, notice that both of these measurements, well, they're measured over here, and I've summed them up. And no matter where I move this point P, the sum of those two things is always the same. Okay, and I can do cool things like I can move the foci closer to the center. If I move the foci closer to the center, the shape is starting to look more like a circle. Until they're exactly on it, in that case it would be a circle. If I move them further and further away, it's going to get more and more stretched out. What do you think is going to happen if I move them outside of the ellipse? That's a sneak preview of what is called a hyperbola. Okay, let me get this back over here, and let's put in these axes. For some reason, one of them is not. There we go. We have both a major axis and we have a minor axis. Now I'm going to put this in one key location so that you can see what the sum of D1 plus D2 is equal to. So if I put this pretty close right here, just take a second and try to decide what is D1 plus D2 equal to. Pause it if you need to. Okay, so you should see that the length of D1 plus D2 is equal to the length of this major axis here. That's because when I put this point right here, I can see that the distance from this focus to that line is the same thing as from the focus to that vertex, vertex 1. Okay, and what I have left over is the distance from foci 2 to that vertex. Well, that just happens to be the piece that's left over. That's right down here. So if I add those two pieces together, I get the length of the major axis. And we're going to call that length 2A, as you'll see in the rest of this presentation. Hey, Rowan. Okay, so as we can see then, call up this pin, this D1 plus D2 is equal to the length of the major axis, which is 2A. That's what this is equal to. So if I were to draw myself, where'd my pen go? A segment that connects all of these points from this point to this point, that segment is 2A. And it's exactly the same length as D1 plus D2. That's what makes an ellipse. So let's look at all of the different parts of an ellipse. Now, you can use the one that is on your flow chart, and you can label these parts on there, or you can draw yourself a new one with all these parts labeled. It's up to you. It's your notes, it's up to you. So, first of all, we have a center point. And the center point, of course, whenever we name it, whenever go to use an equation and stuff, this is going to be h comma k. Okay. It is the intersection of the major axis and the minor axis. I did that. Not every single one is going to have a horizontal major, but the one in this picture is. Okay. Then we have two other points. We have the two foci. And notice that the foci in the center and the vertices, they're all on that major axis. Okay? And here, let me point something out here. Notice that the word major has an A in it. And we know that the major axis, its length is 2A. It has an A in it. Alright? So the foci, the center, and the two vertices, they're always on the major axis, which is always the longer of the two axes, as you'll see right down here. Major axis is always longer than the minor axis. The co-vertices, this is the part that's over here at the top, the co-vertices are always the endpoints of the minor axis. And we're going to use 2b for the length of the minor axis. So the length of the minor axis is 2b. The length of the major axis is 2a. And then finally, the distance between the two foci is going to be 2c. Okay. Now, if you go back to your flowchart again, you don't have to copy all this down. It's all down there for you. Here I have myself a vertical major axis. Let's digest all the points and stuff that go with it. So, again, my center point, I'm using HK. If I have a vertical major axis, and remember, for the major, this A always goes with the major, and if I'm going up and down, it's the y-coordinate that's changing here. So I start with K, and I add A to it to get up that way, and I subtract A from it to get down. Okay, so that's where the two vertices are. If we have a vertical major axis, we must have a horizontal minor axis. And that's going to be the x values are going to change. So here I'm going to add b or subtract b, this time from the h coordinate. And that's what the one at the bottom is saying here. And then finally, the foci, remember the focal length here from between the two foci is 2c. So from the center point straight up is going to be k plus c because we're going vertically, or k minus c to go downwards. Okay, let's practice these points on all of blah, 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 all of these words. And just like with the parabolas, it's probably going to be helpful if we sketch ourselves a little picture to go with it. So the vertices of an ellipse have coordinates 5, 7, and 5, negative 1. So this is vertices. Remember, this always goes on the major axis. Okay, which of course is going to be 2a. Let's sketch this thing out here. So I've got 5, 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Right there is one of the vertices, and then down 5, negative 1 here is the other vertex. Is the major axis of the ellipse vertical or horizontal? And I can see from this diagram that it's going to be a vertical one. How could I have been able to tell that by just looking at the 2 points? Well, these two x-coordinates stay the same. If the x-coordinates stay the same, your y's are changing, you're only going up and down, that's vertical. What are the coordinates of the center of the ellipse? I just have the coordinates of these two vertices, 5, 7, and 5, negative 1. To get the coordinates of the center, that's the midpoint. It's halfway in between those two. So the midpoint's the average of these two coordinates. So the center point is going to be, well, 5's never going to change. The x-coordinate's not going to change. Now for the y-coordinate, I'm just going to take the average of those. 7 plus a negative 1 over 2, which that's 6 over 2 is 3. So the center point is at 5, 3. 5, 3, which is right there. There's the center point. Okay, what is the length of the major axis? The major axis is the one that we just plotted, and its length is 2a, like we saw. And all I'm doing is taking 2a, saying that it is from 7 minus a negative 1 down here at the bottom, which makes the length of this thing 8. If I wanted to, I could get a from that by just dividing it, and so a is equal to 4. Here's a question. Could I get c and b from it? No, I couldn't, because I don't know how wide this ellipse is going to be, so I can't determine any other information from it, just what I've gotten here so far.